Part 2 of our essay overview is to figure out how atomic size, our atomic size is going to change when we have ions, and then again use those size properties to explain all of these other definitions. Let's get started. Order the atoms in the following groups from smallest to largest. Now here we have some ions as well, so we're going to go through the same exercise. But now we need to figure out how the ions are going to play in there. So when we look at the number of shells, oxygen has 2 shells, so does the oxygen ion, oxide. Magnesium has 3 shells. Magnesium 2+, though, lost a shell when those 2 electrons, so now it only has 2 shells. So clearly here we get magnesium is the largest atom. All right? But now we need to compare the others. Oxygens each have 8 protons, and then the magnesium has 12. Okay? So this sounds strange, but this magnesium ion has a lot more protons than oxygen, so that's going to make it a lot smaller. 2 shells pulled in by 12 protons. This has a really high effective nuclear charge. Therefore, magnesium 2+ is going to be my smallest atom. So the positive ions, we need to be very careful. They get smaller. They lose a shell. So now we're comparing them to smaller atoms. And because they have more protons, even though they lose a shell, they're often smaller than all the other things in the other rows below them. So magnesium is a 2+ ion. Now we look at the oxygens. And there's a trend here we need to catch here. If we added electrons, what's actually happening is we're making the electron cloud bigger. So our negative ions are going to be larger than their parent ions, where the positive ions are actually getting smaller, which kind of makes sense. If you add electrons, it gets bigger. If you take electrons away, it gets smaller. That leaves us with a magnesium atom with 3 shells being the largest. All right, next group. Magnesium 2+ again has 2 shells. Iodine has 5, or iodine has 5, and lithium has 2. So now we've got 2 sets to compare. When we look at the protons to figure out the effective nuclear charge, magnesium has 12 again. Iodine 53, but I don't really need to compare these because it's just I'm comparing iodine to iodine. You can see that those 53s are not really a factor there. It's just that negative ion. But the lithium, I will need to compare that to magnesium. Lithium only has 3. So again, both of these guys have 2 shells. You need to state that because that's the only way that we're going to compare their effective nuclear charge. And magnesium has more protons, so it has a higher effective nuclear charge. Magnesium is the smallest because it has the least number of shells with the highest effective nuclear charge. Those are the vocab words you're using. Lithium will be the second, and then iodine, and then iodide, the ionic version, is the largest. Okay, last set. Here we go. Look at the number of shells. Sulfur has 3, sulfur ion. Chlorine ion has 3. Argon 3. Potassium plus lost a shell, now it has 3. Calcium now has 3 as well. So we can kind of see that that is not a factor here. So they all have the same number of shells. So we look at protons to do the effective nuclear charge. Sulfur has 16, chlorine 17, 18. Here we've got a series, 19 and 20. And they're all isoelectric. They all have the same number of electrons in the same spots. But here's where we can see that the calcium has more protons. It has the highest effective nuclear charge. It's going to pull them in tighter. So my trend, calcium is the smallest, potassium, argon, chlorine, and then the sulfide is going to be the largest. Here's a trend for ionization energies. So ionization is the energy needed to remove electrons. So we're only talking about making positive ions. And generally you can see the trend as the atoms get bigger and bigger and bigger, it requires less energy. That's because as the atom gets bigger and bigger and bigger, the electrons are farther away from the nucleus. So it's going to take less amount of energy to pull that one off than it is one down here close to the nucleus. So in general, farther away from the nucleus they are, they're easier to remove. Okay? And then we can see even in a row, as it gets from, say, lithium to neon, that the atoms are getting smaller and smaller and smaller and smaller because the more protons are pulling those two shells in tighter, the energy goes up. So we can see that trend here. What I do want you to see on this graph, though, is there are exceptions. Now, you will never need to predict your exceptions, although your homework problems do love to point them out. But if we look at where the exceptions are, lithium, beryllium, and then boron's a little easier. What's happening there? Sodium, magnesium, aluminum's a little easier. Okay? And we just have this jump. It's kind of in the same spot. Here we've got d electrons, but we've got this little jump here. What in the world is going on? Well, this is where we get new subshells. Okay? So after beryllium, that's the 2s. That's a full subshell. But then when I get to boron, there's one electron there. That one electron all by itself in its own little subshell is actually pretty easy to get out. So we get these breaks between the s's and the p's. There's the break. That p1 electron is actually really easy to get out. And then we continue. Boron, carbon, nitrogen, oxygen's a little easier. There's another change. Aluminum, silicon, phosphorus, sulfur's a little easier. There's another one. So there's another break here. And this happens at between 3p3 and 3p4. So if we look at that one, 3p3 has 3 electrons all in their own individual orbitals. Okay? Now once you put that 4th one in, something about just having that extra, now you're forcing them to be paired up, actually makes it a little easier. If we look here at oxygen and sulfur at the P4 position, it's a little easier to kick that one out than it would be to kick out the one for phosphorus. That's because it's a half-filled subshell. And half-filled subshells are actually more stable than having like 2 or 4 electrons in them. So they kind of resist the electrons coming out of them, and they don't really like that extra. Just if it's just going to be one extra, it's really easy to kick it out. So again, you're not going to need to predict these trends, but there are exceptions, and they happen, 2 things to write down, between subshells, S's and P's, and at half-filled subshells. That can be in the D5 position or the P3 position. So there might be, you might see them. I don't think you'll ever be asked about them specifically, but if given them, you could at least justify it if they gave you the data. But let's just stick with standard ones. Which atom would require more energy to remove an electron? Why? Sodium or chlorine? Well, both of those guys have 3 shells. Okay, but sodium or chlorine is smaller because chlorine has a higher effective nuclear charge than sodium. So chlorine is a smaller atom. The electrons are closer to the nucleus. It's going to take more energy to remove them from smaller atoms. So lithium or cesium? Well, lithium only has 3 shells. Cesium has 6. The smaller atom, lithium, is going to be take way more energy to get the electrons off because they're very close to the nucleus. Write equations for the first and second ionization of sodium. Explain the trend. Okay, well, ionization is removing electrons. So we can write these as the first one, I1, the second one is I2. Sodium turns into sodium plus an electron. And the second one means I'm starting with a positive 1 ion, and I'm turning into a positive 2 ion. So I'm taking off another 1 electron. Notice that though, this is a 10-time energy jump. So we kind of just casually know that sodium is a +1 ion, and we know that it does that because there's only 1 electron in its valence shell. So we're comfortable with that. But here's the real reason why. Why doesn't it form +2 ions? Well, it's a very simple answer. Everything in chemistry is related to energy. It takes too much energy. You could do it. If you had this much energy, you could easily take that second one off. But it requires a lot of energy, and other things will happen before this when you have that much energy. But if you're in the sun, or inside a star, none of the atoms actually have any electrons because all the energy pulls off all the electrons. So you could actually get, for sodium, up to, you could get the equation all the way for the ionization of the 11th electron. Take all of them off, and there's a huge energy requirement for that, but inside the sun it happens. All the atoms do that inside the stars. So we just want to be able to write simple equations and then explain this jump happens at energy level breaks. And we could also write these equations for other processes too. This is ionization. We could do the electron affinity ones or some other ones that are described. So here's an electron affinity. Which ones have the most exothermic electron affinity? Don't let the words fool you. Things come together are exothermic. Energy is released. Electron affinity is now making negative ions. Okay. Electrons are going to be more attracted to, again, smaller atoms. So we just need to know which one of these is smaller. Bromine or selenium. They both have 4 shells. Bromine has more protons, higher effective nuclear charge. Bromine is smaller. Bromine is going to attract those electrons better. All right. Now it has a higher negative number, but that's just a magnitude. It's not a lower number on the number line. It's just the negative means exothermic, not a big deal. But it is more exothermic. It means the electron is more attracted to that bromine. And just getting a quick visual here to wrap up with electronegativities. Electronegativity is the protons, the nucleus of one atom, attracting the electrons of another atom. Okay? So it's attracting those guys. What that means is smaller atoms can get closer. The second atom here, this hydrogen, can get closer to the nucleus of a small atom, fluorine, than it can to chlorine. There's a larger distance here, so there's a weaker attraction to that nucleus, because that nucleus is what makes the bond, that attraction to the nucleus, valence electrons to nucleus. So my smaller atoms are going to have a tighter attraction, stronger bonds, higher electronegativities than the larger atoms. So just to give you a visual of, that's actually what we mean by bond, is the nucleus of one atom attracting a second atom's electrons. And that'll kind of wrap up our trends for the day.